So today's speaker will be Professor Aimee Morgans. She is currently a Professor of Thermofluids at Imperial College London in Department of Mechanical Engineering. She received her PhD in 2003 from Cambridge in aeroacoustics. And following that, she held an Royal Academy of Engineering Research Fellowships in Thermoacoustics. In 2007, she moved to Imperial College, initially as a lecturer, where she is currently a full professor. Her research is focused on dynamics and interactions of sound, flames, and aerodynamics. She had held an ERC Starting Grant in the past, and currently she holds an ongoing ERC Consolidator Grant on acoustic flow interactions for thermoacoustic instability predictions, especially in low emission combustors, which I believe will be also covered in today's talk. So with that short introduction, I hand over to Aimee. Thanks.
Thank you very much. And thank you very much for inviting me here today. Okay, so the outline of the talk then. So I'm just going to explain a little bit what thermoacoustic instability is and why it's a big deal. I'll then talk about why multi-scale prediction methods are used to predict it computationally. And then I'll come on and describe some of our work on acoustic flow interactions, focusing especially on the flow passing through area changes and entropy noise. And then at the end, some conclusions. Okay, so first of all, what is thermoacoustic instability? Well, if we have a flame, this little Bunsen-like flame here, and we send sound waves at it, like in this experimental rig from EM2C lab in Paris. So there are loudspeakers forcing this flame from underneath. We can see how the flame front responds, and it's this little conical flame front that we're interested in. So it's this one here. Okay, so that should show you that when you send sound waves at a flame, you perturb the flame front. So the next thing is what happens when you have a perturbed flame front. And so these are simulations from a group in Melbourne in Australia. And you can see that when this flame front moves, you can see pinch off occurring. And the important thing is that it's generating new sound waves moving away from the flame. So we have a two-way coupling. So sound waves hit a flame, they cause unsteady heat release rate, and that causes new sound waves that move away from the flame. And when the flame's inside a combustor or any kind of enclosed volume, the sound waves, the acoustic waves, can reflect from the boundaries and come back towards the flame. You'll see that this third picture looks very much like the first one. And so this two-way coupling can give rise to a positive feedback, whereby every time we kind of go through the cycle, the oscillation amplitudes can successively increase. And that's what we mean by a thermoacoustic instability. So this is a former postdoc of mine, and he's about to put a quartz tube open at both ends, so just an open tube, over a small Bunsen flame. And you'll get an idea for the really simplest kind of thermoacoustic instability. I hope you can hear the sound from the... So thermoacoustic instability then, so you can see the kind of vibration and oscillations that happen just with a tiny laminar flame inside a tube. So thermoacoustic instability then is a big deal because it's plagued historically the design of both gas turbine and rocket engines. So going right back to the F1 rocket engine for the Saturn V moon landings many decades ago, they actually had to carry out over 2,000 full-scale tests of the rocket engine to eliminate thermoacoustic instability. So it was a really expensive problem. Over recent decades, both gas turbines for electricity generation and aero-engines have suffered especially the propensity to thermoacoustic instability when you try and burn under low NOx conditions to reduce your NOx. Future rocket engines, and I might just, oops. And this is just an example of one. I'll talk more about another one later. Future rocket engines are also susceptible to thermoacoustic instabilities. And I just want to mention that with gas turbines, there's a big move towards carbon-free fuels like hydrogen and ammonia. And they, again, appear to increase propensity to thermoacoustic instability. So the situation industrially at the moment is that it's not possible to take a combustor kind of design on paper and to say, this will suffer instability definitely at these frequencies, and this is what we have to do to eliminate it. So normally it kind of becomes apparent how much of a problem it will be at this sort of demonstrator engine stage. And then it's very costly to sort out. And this picture in the bottom right shows the kind of damage that can happen when you try and run with thermoacoustic instability. So you have to make sure that you're able to operate without them to avoid this kind of damage. So part of the reason why predicting thermoacoustic instability has been so difficult is because there's a really huge range of length and time scales involved. So we talked about the acoustic waves and the flame interacting. The acoustic waves, so thermoacoustic instabilities generally happen at low frequencies, often a few hundred hertz. And the acoustic waves at those low frequencies have got really huge wavelengths, often of several meters or more. And at the same time, what's going on at the flame front, the wrinkling and the chemical reactions has got tiny length scales, less than a millimeter. And so to get a computational method which resolves all of these length scales adequately is very, very expensive. It also points to using multi-scale treatments for the simulation. And what we specifically mean there are that the acoustic waves with the long wavelengths, we treat one way, and that's where we use our analytical models. And that allows us then to direct all of our CFD resources, typically using high performance computers, at capturing the response of the flame unsteadiness, which is a lot more complex. And then we can couple, and the fact that you don't have to include the acoustic waves in the whole system here means that you can really focus on the flame region and you save simulation time. So then by coupling the CFD simulations for the flame and the analytical models for the acoustics, you get your multi-scale prediction. So going into the analytical methods for the acoustic waves typically are modeled as being both linear and low dimensional. So what we mean by linear, so you can see a kind of typical profile of some variables, say pressure against time for a thermoacoustic instability. So you've got some kind of transients at the start, then it's a linear instability, so your envelope is growing exponentially, and that can't happen forever. So eventually nonlinear effects kick in and you get typically limit cycle oscillations at a given frequency and amplitude. So pretty much always the case for gas turbines and very often the case for rocket engines, the pressure fluctuations in this limit cycle are less than 10% of the mean pressure. And what that means is that the acoustics are behaving linearly, even in the large oscillations, and the nonlinearity is coming from the flame response, not the acoustic waves. So that justifies the kind of linear assumptions. Then for the low dimensional, what we mean by that, so if we put a three-dimensional sound source inside a duct, I've got a simulation of what happens at low frequencies. So this is our three-dimensional sound source. And what we see is that at low frequencies, the duct isn't able to sustain the three-dimensional waves. You just get plane waves very quickly moving away from the source. So these are plane waves in a kind of straight duct. And very often we have annular geometries as well, and then we get circumferential waves. But we know how to deal with those as well mathematically. And then this is just one thing that I want to mention, just kind of background theory that might help sort of understanding some of the rest of the talk. So we model our acoustic waves as linear and low dimensional. If we look at a duct flow, so this is a duct with a subsonic mean flow, it's been shown that the linearized Euler equations show you that the flow disturbances can always be represented as two acoustic waves in a subsonic flow moving in either direction, an entropy wave which convects with the mean flow or advects with the mean flow, and a vorticity wave, which advects with the flow. So you've got two acoustic waves which propagate at the speed of sound relative to the flow, a vorticity wave and an entropy wave. And these are completely decoupled if the duct isn't changing area and there's no heat release rate or heat transfer. So in a straight duct with no heat transfer and no heat release rate, we've got two acoustic waves, an entropy wave and a vorticity wave, and they're completely uncoupled. So the acoustic modeling, then we kind of build up the complexity. So if we're looking to model a combustor, we might have a plenum, some premixed ducts, and then the combustor itself with the flame sitting at the upstream end. So the acoustic modeling simplifies the geometry into a connected network of simple modules. You've got your acoustic waves going in either direction in each. You can link them across modules using linearized flow conservation equations. So we can link our wave strengths. We can apply acoustic boundary conditions at either end of the combustor. And then we're just left with the kind of problem of the flame. How are we going to incorporate the effect of the flame on the acoustic waves? We know that the flame responds to the acoustic waves and it also generates acoustic waves. So for how it generates acoustic waves, again, we can use linearized jump conditions from the linearized flow equations, conservation equations. For how it responds to acoustic waves, the first thing to mention that's actually relevant to both how it responds to and how it generates acoustic waves. If we look at the kind of possible flame shapes, we've got conical flames, V-shaped flames, M-shaped flames, multiple flames. These are all for laminar flames. They can be similar for turbulent flames. You get more sort of wrinkling at the flame front. The important thing is that in all of these cases, the sort of spatial extent of the flame is much less than the acoustic wavelengths typically. And that means that you can model the flame as a discontinuity as far as the acoustics are concerned. So a discontinuity in acoustic wave strengths. And so when we apply our flow conservation equations to work out the acoustics that the flame are generating, we can apply them across essentially a discontinuity in space. For how the flame is responding to acoustic waves, that's where we feed in a flame model into our low order network code for the acoustics. And so for our flame model, what we want to know is if we force the flame from, say, upstream with acoustic waves with velocity perturbation U1 dash, what is the response of Q dash? And Q dash is across the whole flame. It's a kind of global response, the unsteady heat release rate. And that's what we mean by the flame model. So we get that from large eddy simulations. So we harmonically force our flame with an upstream velocity perturbation. And we do this at different frequencies and amplitudes. And we look at the gain and phase shift needed to get the unsteady heat release rate. We typically you can use linear models and then you get a frequency response or a Bode diagram. We know that the nonlinearity is associated with the flame, and it turns out that weakly nonlinear flame models capture the flame response very well. And so that means that if you force your velocity at a certain frequency, 100 Hertz, say, the main response you get is also at that frequency, but that the gain and the phase shift depend on not just the frequency, but also the forcing amplitude. And so a weakly nonlinear flame model, a flame describing function as we call it, has a kind of family of frequency responses for different forcing levels. Generally, you see the gain drop down as you increase the forcing level, and it's that kind of gives you your saturation. Well, that's one of the mechanisms. So when we put that together, so we've got our low order models for the acoustic wave propagation. We get our flame model from large eddy simulations or even from experiments. And when we put them together, we've got our low order thermoacoustic network model. So this is a combustor, again, from Paris EM2C lab. And you can see how we sort of simplify the geometry modules. And then this bit goes downstream and is this large thing here. So it offers physical insight because we can always see what the acoustic mode shapes look like and how the boundary conditions are interacting and so on. We'll see now that there's good accuracy for lots of cases and that it's very, very fast computationally compared to doing a full CFD where we resolve the acoustic waves in the whole combustor as well as the flame. So we've got a kind of low order network code that we've released open source. This shows you the kind of predictions we can get from it. So if we put in a linear flame model, we can predict how stable the thermoacoustic modes are and their frequencies. So for example here, the modes are given by where this kind of goes very low. So these red, white dots are the modes, the thermoacoustic modes. These are the frequencies on the left-hand side. And then on the x-axis, we've got the growth rate. So if the growth rate is positive, the mode is unstable. And if it's negative, the mode is stable. And so you can see what we're predicting here is an instability at about 160 Hertz. So we've applied this to probably three or four different kind of experimental combustors that are available in the literature where they've measured thermoacoustic instability. I've got results here for the most complicated. So they kind of varying levels of complexity. This is the most complicated one we've done predictions for. It's a combustor from DLR in Germany. It's based on a Siemens SGT 100 combustor. And so you can see there's lots, there are pre-mixed ducts, the flow features, there's a central vortex core, processing vortex core, lots of kind of industrial complexity flow features. And when we do the large eddy simulations to get the response of the flame to forcing, and we put that in our low order network representation for the geometry shown here, we're able to predict that the combustor is unstable with an instability at 209 Hertz with an amplitude measured somewhere on the combustor of 4,970 pascals. And that sort of works, that's predicted very well compared to the experimental measurements. So we are seeing a lot of success with this coupled approach. However, I would say that when we go to kind of real industrial complexity combustors, there are many acoustic flow interaction effects that aren't, the treatment of them is currently too simplified in the low order network models for the acoustics. And so we need to kind of build up the complexity of the models to capture some of these. And so, for example, in this picture here, you can see that the flow field from the flame to the exit of the combustor is undergoing a slow area change. There's also going to be an axially varying temperature change. The separated flow isn't properly, or we don't understand how it properly should be accounted for yet. At the end of the combustor, the acoustic boundary condition is not that simple because it's not just say a nozzle. You've actually got a stator row turning and accelerating the flow that's not properly accounted for. And the combustor walls might have little holes in them for cooling, but they also provide acoustic damping. So this is kind of really what the Consolidator Grant is about. So the first few letters of affirmative are all about acoustic flow interaction models. So I'm going to focus on two of these today. Both have got kind of two bits to them. So the first is going to be flow passing through area changes. So I've got two combustors, quite a simple combustor and then a more complex combustor that we've looked at. For both of them, so the flame front sits here in the simple combustor, and you can see that the flame sits just after so the flow is coming through in this direction. And the flow then is just after a sudden area expansion. And again, for this more complex combustor, the flow is coming through, the flow is coming through in this direction. And so the flame establishes itself after, again, a sudden area expansion. So what we found, there are different approaches to modeling the acoustics in the literature. And we found that we were predicting the sort of thermoacoustic limit cycles pretty well, whereas some methods which say neglect the mean flow were not predicting them so well, and they were having to put in kind of empirical damping factors. And so that kind of led us to think that what's going on at these area changes, especially the area expansions, is actually quite crucial. And so we want to know more about specifically the acoustic damping that occurs. So we've done some modeling for that. So we consider a simple abrupt area increase with a mean flow, a subsonic mean flow. So we account for acoustic entropy and vorticity waves, but actually we only assume that we can send in acoustic waves and entropy waves, and we assume that what we've got coming out is only acoustic waves and entropy waves. So any vorticity waves are generated within the zone and kind of dissipate before or are dispersed before they get to the end of the sort of analysis zone. So it's this light blue analysis zone that we're interested in. So we assume that upstream of the analysis zone, the waves are all 1D, and downstream, they're all 1D. And that we've got an acoustically compact sort of zone where there's more complex flow physics going on. And that's what we want to model. So we look at initially a quasi-steady model where we're applying our linearized flow conservation equations across this flow area increase. And so we apply the conservation equations of mass, momentum, and stagnation enthalpy. And crucially, we kind of, when we do that, we assume that the mean pressure on this back face here, which is kind of like an annular shaped back face, if these are two cylindrical ducts, we assume that that back face pressure is equal to the pressure just upstream in the flow. And this is a kind of really classic assumption that you apply to separated flows in lots of different applications. And we're applying it here, and we're going to investigate it in a little bit more detail. And again, when we apply the linearized flow conservation equations for the perturbations, we assume that the pressure perturbation just near the downstream face, back face, is equal to the pressure perturbation just upstream. So we're applying that kind of constant pressure in both the mean and the perturbations. So in the mean, we can check it using RAND simulations. We can look at what we call the pressure loss coefficient, which is the mean upstream pressure divided by the mean backplate pressure. We can do this for a variety of area expansion ratios, or I guess contraction ratios. It's written as AU over AD. So I've got them here for the middle one, but we consider other ones as well. And we can set the upstream flow to different Mach numbers. And so this is a table showing K. And what we see is that basically the upstream pressure and the backplate pressure are the same to a high degree of accuracy for all of them. And if we zoom in a little bit and look at the pressure, we see that the pressure is indeed kind of constant across the expansion, and then you get a slow pressure recovery. So in terms of kind of checking what's going on with the predicted acoustic waves, we're now going to focus very much on what we call the acoustic absorption coefficient, and that allows us to really focus on acoustic damping or generation. So the acoustic absorption coefficient is this thing here that I'll refer to in kind of quite a bit in the talk, delta, big delta. And it's 1 minus the outgoing energy flux divided by the incoming energy flux. So you can see that if you've got no, and so outgoing comes from FD and GU, and incoming means FU and GD. So if you've got no outgoing acoustic energy flux, you can see that your delta, your acoustic absorption coefficient, is going to be 1, and that's full acoustic absorption. If you've got delta equals 0, that means that your outgoing and your incoming acoustic energy fluxes match. So this is 1, we've got 1 minus 1 is 0, so you get no acoustic damping or generation. And you can get situations where the acoustics kind of extract energy either from the mean flow or from vorticity or entropy perturbations, and then the outgoing energy flux can exceed the incoming, and we end up with a negative acoustic absorption coefficient. So if we look at what our model is predicting across our flow expansion, so we've got it as a function of the upstream reflection coefficient for different Mach numbers and different area expansions. So very often our upstream reflection coefficient, so we know, for example, that a reflection coefficient of 1 with a phase of pi corresponds to something like a closed condition. And if we've got a sort of big contraction somewhere upstream, which often we do, that's reasonably realistic. So what we can see is that basically we get an acoustic absorption coefficient that's quite low quite close to zero. So we're not getting a huge amount of acoustic damping or generation, except we're getting a fair bit of damping close to this kind of closed upstream boundary condition. And that becomes more pronounced as the Mach numbers increase. Interestingly, when we get to very high Mach numbers, that's even more kind of pronounced, that we can get very high acoustic damping. But there's also this little zone over here, which you would see if you kind of zoomed in on some of the others as well, where you can really see that you've got a little zone where certain reflection coefficients give acoustic generation as well. And so that's something quite new, that you could possibly have an area expansion where you're getting small amounts of acoustic generation. It would be quite worrying from a thermoacoustic point of view. This is the validation against the simulations. We use linearized Navier-Stokes equation solver. Don't worry too much about the difference between the C and the U. The left-hand side of each is for a coupled solver and the right is for an uncoupled. So we're just comparing two different numerical solvers. So if we just take the coupled one, the full one, we can see if we go back and compare to the model results, we're basically seeing exactly the same behavior in the numerical results. Small quantitative differences, but we're capturing all of the main features. It was a quasi-steady model that we were talking about here, so we might be quite interested in how it behaves if frequency is increasing. Here I can see we've defined what we call a scattering matrix linking outgoing acoustic waves to incoming acoustic waves, and we've got 4 components, which is shown in these graphs. The arrows are the predictions from the quasi-steady model for different expansion ratios or contraction ratios. And the dots are from the simulations at different frequencies. And so what we see is that the model at low frequency is a very good match to the numerical predictions, arguably all the way up to a Helmholtz number of 1. So that means that all the realistic frequencies we're interested in. So that all shows that the quasi-steady models, which assume that the pressure is constant in both the mean and the fluctuations across the area expansion, work really well. So they're capturing the acoustic damping very nicely, very accurately. The acoustic damping itself depends very strongly on Mach number and acoustic boundary conditions. And surprisingly, we've seen that an area expansion can actually generate acoustic energy. So moving on now to acoustic models for smooth area changes. So if we've got a duct with a mean flow and we've got our temperature and flow cross-sectional area varying with our axial distance x, you can see straight away that that's going to affect the acoustic waves, because the speed of sound that the acoustic waves are moving with relative to the mean flow depends strongly on the temperature. So we're interested, so this temperature and this area variation are going to be directly linked if the mean flow is isentropic. If we've got, say, heat transfer through the walls, if it's a non-isentropic mean flow in some way, these two can vary independently. And so we want to develop models for how the acoustic field in such a duct kind of varies with X that account for the mean flow. And the first thing we want to do is to restrict this to plane acoustic waves. We saw the plane waves earlier, so we don't want to account for radial or transverse modes. We want the acoustic waves to be planar, and that means that we're requiring low frequency, which is something that we need to come back to. So if we're looking to develop these models, we can start with the linearized Euler equations in mass and momentum. We can assume that the coupling between the entropy and the acoustic waves is weak. And then we can basically rearrange the linearized Euler equations so that we just get an ordinary differential equation in pressure, ODE in pressure. So P hat is pressure in the frequency domain. So the coefficients of this ODE, this is a kind of new ODE. The coefficients depend on the Mach number, the wave number, then alpha is the non-dimensionalized area change with X, axial area variation, and beta is the non-dimensionalized or normalized temperature variation. So both alpha and beta depend only on X. K0 depends on Mach number and X. Frequency and X. And so these B, C, and D coefficients in the ODE depend only on frequency and axial location X. So we solve them using something called a WKB approach. So we assume wave-like solutions and substitute into the differential equation to get the coefficients. The WKB method is a high frequency method. So there's a high frequency assumption. So essentially it's assuming that the axial distance over which in some sense the temperature and area change is much larger than the acoustic wavelengths. And so that means that we've got a kind of requirement on our frequency that it's got to be low enough that the waves are 1D, but high enough that we satisfy our WKB requirements. And when we put in kind of typical area and temperature changes, we find that there is a kind of intermediate zone where we can satisfy both of these, where it is worth developing the models using this method. So the models end up showing us that you can represent the pressure at a given location in X and given frequency omega in terms of two wave strengths. So we know that in a constant area duct at constant temperature, these would only depend on omega, they wouldn't depend on X. We've now got expressions which do depend on X, and they're not too bad, so they're fine to code up in MATLAB. And we've got coefficients C1 plus and C1 minus that depend on boundary conditions. So going back to our acoustic absorption coefficient, delta, and just a reminder on the left-hand side of what this is, we can look at, so the top three plots are kind of shown by these little red schematics. So they're constant area ducts, and we're interested in whether we're cooling or heating them. The bottom three plots are constant temperature ducts, which are either converging, straight, or diverging. And so we were able to have a look at what's happening with the acoustic damping under these conditions. And this has all been validated against linearized Euler equations. So going to the bottom plots first, we see it's quite a complex picture that whether we are generating acoustic waves, the yellow color, or absorbing them, damping them, depends on kind of how aggressive the area changes. When we are looking at the ducts where we're either cooling or heating them, we see quite clearly that we get acoustic generation when we are cooling our ducts, and we get acoustic absorption when we're heating our ducts. And this seems to be quite a clear link that comes out if you look at the equations as well, if you've got a constant area. And all of this is kind of feeding into a project that we're just starting with reaction engines. So reaction engines are a UK-based company. They are developing what they call a Sabre engine powered by hydrogen. And it's an engine that can work in either air breathing or rocket mode, and it can switch between them. And the idea is that it's going to kind of facilitate kind of low Earth orbit space flight. The technology is based on quite complicated interacting thermodynamic cycles, including a helium cycle. So if we look at what the Sabre engine will look like, it's got a supersonic air intake. And so that means that there are shock waves at the inlet, and the mean temperature is going to increase across those shock waves. They've then got a pre-cooler, which is one of the main technologies they're developing, basically a big heat exchanger. The important thing about this supersonic intake is that when the engine isn't traveling fast enough, so soon after takeoff and at relatively low altitude, there aren't the shock waves present to generate that temperature increase. But the interacting thermodynamic cycles require the air there to be hot. And so that's where they have to turn on a component called the pre-burner. So the whole thing is powered by hydrogen as a fuel, and that includes the pre-burner as well. The pre-burner is an extra hydrogen set of flames they can turn on. So it heats the air when the heating's not coming from the shock waves. or the temperature increase isn't coming from the shock waves. And then they use some heat exchanger tubes to take that to the thermodynamic cycles that need it. And the heat exchanger tubes actually now extend downstream. And so what they're quite worried about are that, is there a propensity to thermoacoustic instability in this region? And if having cooling between these heat exchanger tubes is actually feeding into the acoustic energy, it's going to make that worse. Okay, so that's it for flow passing through area changes. And I want to talk about entropy noise, the second kind of technical part of the talk. So entropy noise kind of always sounds quite strange. So we looked at the video earlier where the flame was kind of moving and generating sound waves. And that's these purple acoustic waves here. But as well as that, an unsteady flame also generates regions of fluid which are hot or cold compared to the mean. So hot spots and cold spots. And these are what we call entropy waves. So entropy waves are based, in this sense, are just temperature fluctuations. So they are the non-acoustic part of the temperature fluctuation. So these just advect with the flow, and they don't have any noise associated with them. They're initially silent. The interesting thing comes if we try and accelerate these entropy waves. So you can see here we've got regions of hot fluid and cold fluid. And when you try and accelerate them, you've got regions of fluid with different densities undergoing a volume contraction. And that means that it acts as an acoustic source. And so this is what we call entropy noise. So these are videos here from the Surfax group in Toulouse. So the top one shows temperature fluctuations being sent into a Condy nozzle. Initially, the bottom pressure fluctuations are just at 0. You can see that when we start accelerating the temperature fluctuations, we generate sound. And this is a big problem in lots of practical combustion systems because the unsteady flame is in the combustor. The combustors have low Mach numbers. And then at the end of the combustion, you've often got a really rapid flow acceleration. So for example, in a gas turbine, this first stator row, the exit there will typically be very close to choked. So you've got the perfect mechanism. You generate entropy waves at the flame, temperature fluctuations, and then you accelerate them. And that generates what we call entropy noise. And so we've been working on this since about 2007, developing various models for how the entropy waves affect and how this part generates noise. So something we've been working on recently is entropy noise through kind of orifice flows. So Marble and Candel had some very early seminal work on entropy noise. And they developed a kind of zero frequency, so quasi-steady, quasi-one-dimensional isentropic model that works really well when you've got gradual area changes like the one at the top, the nozzle. And actually, it's easy to relax, or not easy, it's now possible to relax the zero frequency assumption because subsequent work has developed methods that allow you to extend this to any frequency, but still with the quasi-1D and isentropic assumptions. Recent experiments by the group at Cambridge, Simon Hochberg's group, showed that this theory just doesn't work when you've got an orifice plate flow. So they've got a combustor where they deliberately, or a duct where they deliberately generate entropy waves, temperature fluctuations, and these come downstream, and then it's terminated by an orifice plate. And the models just don't work for predicting the entropy noise. And so we're interested in understanding why. So we're going to, if I got you. So if we focus on a flow expansion, the top. So this is the orifice plate flow. You can see the velocity going through it. The bottom movie shows the entropy waves. And so what we can see quite clearly are that the entropy waves start out being one-dimensional, and the flow starts out looking like a good approximation to isentropic. But then at the expansion, you get this large flow separation, and you can see that the entropy waves no longer look 1D. And so we're going to focus very much on the expansion. So we've developed a new acoustic analogy for entropy noise. So what we mean by that, what a reminder of kind of what acoustic analogies are. I'm going to start kind of with just one slide, a reminder of Lighthill's acoustic analogy. So basically you start with the flow conservation equations that you're familiar with, mass and momentum here. You consider disturbances in a uniform medium at rest. When you substitute those in, and you can kind of substitute one equation into another, you can combine them. So it's an exact rearrangement of your flow conservation equations so that you get a wave operator on the density fluctuation on the left-hand side. And that wave operator is telling you how your density fluctuations propagate. So you call that the propagation term. And then all the terms that are left go on the right-hand side, and you think of those as acoustic sources. And that's where this, what we call the Lighthill acoustic source term comes in. And so if you can use an acoustic analogy, it helps you predict sound more kind of computationally efficiently, and it gives you some physical insight into what's going on. So we kind of developed a new version for entropy noise. So we use stagnation enthalpy as our variable. The stagnation enthalpy fluctuation turns out to be the best variable when you've got a mean flow. I seem to have lost some things here, but basically these first two terms should have this BA by them. These are due to the acoustics if there's no vorticity. And this last component is due to the entropy. And so this BA dash is the first two terms. So we decompose our stagnation enthalpy fluctuation into an acoustic and an entropic component. And I should just mention this is exactly the same as what's often called H0 in thermodynamics. And then the details are in our recent JFM Rapids paper, so I'm not going to go into them, but basically we can rearrange then the flow equations so that we get a convected wave operator acting on the acoustic part of stagnation enthalpy on the left. And so that's our kind of propagation term. And on the right, we've got our acoustic sources, one in terms of vorticity and one in terms of our entropy, S dash. And so this acoustic analogy kind of generalizes the work of people like Fuchs, Williams, Morphy, and Howe. There's BA. So we apply that to the flow expansion. So once you've got the equation in terms of the propagator and the source terms, you can combine that with the Green's function for the operator, for the propagation operator in the geometry that you're interested in. In this case, the expansion geometry, so one cylinder expanding into another. For the source terms, for the vortical source, we assume that we've got a cylindrical vortex sheet that's straight. And for the entropic source, we solve the convection, the ds dash by dt is equal to 0 using the mean flow field. So we've also done some simulations using a linearized Navier-Stokes solver to check our solutions against. And so you can see sending in the entropy wave, the corresponding acoustic wave at low frequencies and at high frequencies. I don't know if I can stop. No. So the important thing here is the graph in the bottom left showing basically the reflected noise that you get back when you send in an entropy wave. So the noise, the acoustics that's propagated back upstream. The Marble and Kandel predictions are up here, the previous theory. You can see that the numerical predictions are in green and our model predictions are the black circles. So you can see that our model is now much better able to predict the low frequency gain of this transfer function, and also the fact that it's got a low pass behavior. We can also go into some of the flow physics, see what's going on. So when we look at our entropy profile, we can actually take a kind of toy profile based on an error function about where the entropy, so you'll notice that in all of these, the entropy wave expands very slowly, and it doesn't really enter the kind of corner recirculation zone at all. And so we can do some toy models where we look at it expanding quite rapidly, but with a spatial delay. And what we find is that this spatial delay can explain the difference between the Marble and Kandel, the previous theory, and the current predictions. And we can also either account for or neglect vortical noise, the vortical noise source, in our acoustic analogy. And we find that basically it barely changes the predictions at all. And so that allows us to kind of say that we can now predict entropy noise for a flow expansion. The entropy noise dominates over vorticity noise in that case, and that the main reason for the deviation from theory is actually because of the spatial delay in the entropy noise source, because of the spatial extent of the flow separation. So the last bit of the talk is just a few slides on entropy noise for blade rows. So nearly all of the work that's been done by both our group and others is on the entropy noise generated when you accelerate entropy waves in a nozzle. So it can either be a straight nozzle like this, or it can be an annular nozzle. And getting good models that give the boundary condition for when you send an entropy wave into a blade row acceleration, only sort of very old zero frequency approaches are currently available. So we want to do some entropy noise modeling for a single blade. So we've got a single blade here, it's non-lifting in this case. The top is temperature fluctuations, so we're sending an entropy hotspot onto the blade, and we see underneath that sound is generated because of local flow accelerations and decelerations. So if we look at the kind of 2D problem, if we take our mean flow to be both compressible and inviscid, then we've got a compressible potential mean flow. And we can then use some of the ideas that were developed for kind of rapid distortion theory in turbulence and look at small perturbations to that. So small perturbations in velocity, pressure, and entropy. And what that allows you, if you then decompose the velocity into an acoustic part, that's the gradient of an acoustic velocity potential, what we call a homogeneous part and an entropic part, it means that you can recast your linearized Euler equations as 4 equations. The entropy one has an analytical solution, the homogeneous one has an analytical solution, and then you just end up with one coupled partial differential equation, which is the one shown at the bottom here, and also here. So it's in the velocity potential phi, the acoustic potential, and there's a source term on the right-hand side that I've written as S, but it depends on everything else and it's got lots of integrals in it. So to solve it, we make various other assumptions. For example, we assume that the blade is small compared to the acoustic wavelengths, but not the entropy wavelengths. So entropy, at a given frequency, the entropy wavelength will be much less because it's a kind of convective term rather than propagation. We assume that the mean flow velocity deviations are small in some sense. We apply Born and Lorentz type transformations, and that allows us to re-express the top equation as a Helmholtz equation with a source term, which we can then solve using a Green's function approach to represent the acoustic potential as a monopole and then dipoles in either direction. And from that, we can get the pressure fluctuation. So we've got numerics to kind of validate that. And so you can see that when the left is sending entropy waves at the blade and the right is the resulting pressure field. And you'll note that the blade is much, much smaller on the right. And these are our predictions for a mean Mach number of 0.2 for a non-lifting blade. As we increase the Helmholtz number, which is the non-dimensional frequency, what we're doing is we're going a certain distance out from the blade, and then we're sort of traversing around at that radius and looking at the directivity of the acoustics. And so what you can see, so it looks quite quadrupole-like at low frequencies and then quite dipole-like at high frequencies. The CAA is computational aeroacoustics, so that's the numerics, and you'll see that our model is giving very good predictions all the way up to the Helmholtz number of 0.1. We find that it starts breaking down at a Helmholtz number of about 0.5. So we want to kind of extend that to flows where to lifting blades and to where the mean flow can't be assumed to just undergo small deviations due to the presence of the blade. We've got simulations for that already, and you'll see that the sound is quite interesting. It ends up looking a bit like a kind of rotating dipole. So this is the entropy hotspot hitting the blade. You see the kind of rotating dipole on the right-hand side. But that's a kind of more complicated problem. And so it looks like the integrals that we were able to deal with analytically before, we may now have to kind of integrate numerically. So that kind of brings me to the end. So we've seen that low order couple predictions offer a lot of promise for predicting thermoacoustic oscillations, and that there's a need for improved acoustic flow interaction models at area changes and for entropy noise. The kind of things we're looking at now are thermoacoustics for heat exchanger tube rows with reaction engines, entropy noise for lifting blades and blade rows. We're very interested in thermoacoustics for hydrogen and ammonia fueled systems. And then for both what we've developed for the area changes, and also we've done a lot of modeling on whole acoustics, we're quite interested in exploiting that for optimization of the acoustics, which has become much more possible with, for example, 3D printing technologies. So I just want to thank all of the PhD students and postdocs. Obviously, all of the graphs and results came from them, and the ones whose work I featured in this talk are named there. And I'd also like to thank my financial sponsors. So thank you very much.